Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be looking at 2 viewer questions all about how to segment grounds in isolated DC-DC converters and how to do this the right way on your PCB. Now I know this is something that I've talked about quite a bit from the circuit perspective, and most of you know the answer to this already, but how do you actually make that happen inside the PCB, especially when you're using an optocoupler to couple signals across a ground gap? We're going to look at 2 different options, whether you should overlap the planes or whether you should physically split them and pass that all the way through the PCB stackup. We're going to look at some examples as well, which we've published in other videos, so make sure to check out the links in the video description for that content. Let's go ahead and take a look at those viewer questions and get started. So before we get started looking at some examples for the 2 different ways to separate grounds when you need galvanic isolation, let's take a look at those viewer questions. First viewer question comes to us on LinkedIn from Amit Parmar. Amit writes, "Hi Zach, first of all, thank you so much for creating such informative videos." Of course, thank you very much for the very nice compliment, Amit. "I'm currently designing a 4-layer PCB that includes an isolated output. For isolation, I'm using an optocoupler, and the isolated output voltage and ground are isolated through a 5-volt to 5-volt DC-DC converter. From my research, it seems that I should cut out all 4 planes to isolate the voltage and ground, ensuring that no traces cross the isolation barrier. Based on your experience, is my understanding correct?" He then provides some additional detail about maintaining some clearances, 3mm gap between the isolated plane and the main plane, and then the optocoupler that he's using only allows a 2mm gap. He also provides some screenshots of his PCB layout so we can review those. So we'll take a look at those PCB images in just a moment. Our next question comes from Marius Pop. Marius writes, "Hello, Zachariah. Please apologize to me that I am bothering you." Hey, don't worry about it. You guys bug me on LinkedIn all the time. "I am writing because I read your articles and I also saw the videos that you posted regarding how to design and fabricate the best 4-layer stackup with Altium Designer." He then says that he doesn't have much experience in PCB layout, but he does have a 4-layer board with DC-DC converters on it. And here you can see the details on his stackup. On the top side, he has signals and the reference or the ground for those signals. He also has some 24-volt signals. And then he has a power ground, a power layer, and then again, his signal ground on the bottom layer. And he gives us a block diagram, which has 2 isolated DC-DC converters, a non-isolated DC-DC converter, and an LDO. We essentially have 2 viewer questions asking the same thing about isolated DC-DC converters, and that is, how do you put those different ground nets into the PCB, possibly on a PCB with 4 layers? Let's take a look at the whiteboard and see what our options are, and then we'll take a look at some examples in Altium Designer and some optocoupler components that enable this type of isolation. So let's take a look at these 2 methods for building a stackup for setting up these grounds in a DC-DC converter where we have galvanic isolation. So here we're talking about 4-layer boards, and so of course the typical 4-layer board is going to look something like this, where we have our prepregs on the outside and then we have our core on the inside. Now in the proposed approach for Marius, his design basically would have ground 1 on 1 layer, ground 2 on another layer, and then we would probably have signal on the top and signal on the bottom. Now in his message, he also mentioned that there is a reference net up here on the top layer. So we would actually also have, we'll call it reference number 1 up here on this top signal layer. And then we have an additional layer down here, which he said was also allocated to ground 1. So we basically have a whole bunch of references in this design, all overlapping each other, as you can see here on the right-hand side of the board. Now the other way to do this in this same structure is to basically take our 4-layer board and cut out some region between the polygons on the primary and secondary side. So we would have our primary ground right here, we would have our secondary ground right here. We would then normally mirror these onto the 3rd layer, as you can see here. And then this would allow for signal and power routing on the top and bottom side. We would then place our optocoupler right across each side of this design, and then we would also place our transformer in this same way. So that way we have our power routing coming directly into the transformer on the primary side, and then coming directly out of the transformer on the secondary side. Now, within each of these structures, we have some capacitance between these different ground nets. And this is important, as I'll discuss momentarily, because that capacitance between each of these ground nets really determines how much noise is going to pass between different parts of your PCB layout. So here, of course, when we have a reference on the top side and then ground on one of these inner layers, we then have some capacitance between these two conductors. We also have that same capacitance down here between these conductors. We also have some capacitance here between these two internal layers because these are different ground nets. Now, how does this compare to the case here where we have our primary side ground and our secondary side ground located on the same layer? Well, here the strong capacitance is going to be across these two ground nets. We'll also have some capacitance here across these two ground nets. Now, there could be some capacitance across the isolation barrier like this, but again, that's going to be a much larger distance and much smaller overlap compared to this case here where we have the two grounds on the same layer. So we basically ignore this cross capacitance because we can expect it to be so small. So in order to decide which of these two configurations to use for our isolated DC-DC converter, we need to compare these capacitances, and then we can get an understanding of how noise will pass between these different nets in this design. Now that we've looked at the options for placing our different ground nets in our PCB, let's take a look at Amit's design. I have Amit's design here on screen, and here you're seeing the PCB layout inside of Altium, and you can see here that he's indicated where the isolation barrier arises for this design. Now you can see here he's indicated the isolated voltage, and I think that means that this blue rail is where the input power comes into the design. It then comes over here to an integrated circuit, which isn't totally visible in this view, but this integrated circuit right here has some separated polygon on this top layer, and he indicates that this is where the isolated voltage comes in. So this appears to make sense. It looks like we have some capacitors up here on this top side. This might be a reference net over here, also on the top side. And then here you can kind of make out the outline of an integrated circuit. Now, if we just go over here and look at the top layer in 3D, you can see where that component is. It's reference designator U11. You can see where pin 1 is right here. And you can see here where we have those polygons on each side of this component. Now, Amit, if you're watching, please feel free to jump into the comments and correct me on anything if I say something about your design that is incorrect as to how you've done this PCB layout. Now, when we look at the backside in 3D, you can kind of see where the polygon is that leads back over to that power input. And I think it's right here where you have this array of vias. If we look at the backside, you can see that array of vias is right here, and that is connected to this large polygon, which then goes over to this terminal block. So here's where you can kind of see the ground separation in one of the internal layers. You can see it's right here below this terminal block, and it's basically this big section of polygon that I'm outlining with my mouse. Now, one thing Amit noted in his message is that this polygon was not split all the way through the stack up. So that means if we go back and look at the PCB layout, we actually do have a full plane here on layer 2. And you can actually kind of make out where that plane layer is. You can see here where the negative portions are visible in green, which of course is the default layer color for layer 2 in a 4-layer board inside of Altium. Now, Marius did not send a full PCB layout. Instead, what he sent was a block diagram, and I have the PDF of that block diagram pulled up right here. So here we can see the structure of his design with the DC-DC converters and multiple ground. We're bringing in a 24-volt input. We have a 24-volt reference net. We then have connections to a chassis spanning everywhere across this isolated DC-DC converter. And then here on the right-hand side, we have our first separate ground net. This is our 12-volt ground. And then here we also have a signal ground. So here we have multiple possible ways to overlap or split all of those different ground nets. You could have some of those nets overlapping, you could have none of them overlapping and have all of them split, or you could have all of them overlapping on different layers. And so I think it's an open question, which one of those should you pursue in this type of design? Now remember, the whole point of splitting the planes or separating the ground nets in an isolated DC-DC converter is to do two things. One of those things is to hit a galvanic isolation specification. And that is, of course, for safety. You don't want to expose the user to high voltage or to high current, or both when they're interacting with your device. The other reason is to control high frequency noise. And how do we control high frequency noise? It's by controlling the amount of capacitance between those two ground nets. Those two ground nets can have a potential difference between them, and of course, when you put a potential difference across a capacitance, you could get some displacement current that flows between those two terminals. That's basically the mechanism that allows high frequency noise on one side of your DC-DC converter, typically on the secondary side, to then flow back to the primary side and eventually back to the power input where it returns to ground, instead of radiating everywhere and creating an EMC problem. Now, as I've discussed in other videos, normally we do this with a Y-type capacitor, and that Y-type capacitor is intentionally placed across the primary and secondary side of your transformer in order to provide that path for high frequency noise. So let's compare the case of placing a Y-type capacitor with using coplanar ground or overlapping ground, and then we can compare that against the typical interwinding capacitance of a transformer. So here on screen, I have a calculator pulled up that shows the coplanar capacitance between two sheets of conductor. So we can use this, but of course, if we just scroll down here, you can see that we actually have a calculator with some inputs. I'm using a width and length of 1 inch, so we basically have 1 inch by 1 inch squares that are separated from each other by 2 millimeters, which was the value that Amit listed in his message. And then we're assuming a relative permittivity or dielectric constant of 4. This comes out to a capacitance of 2.666 picofarads. Now, typically with microstrip routing or routing on the surface layer, the actual or the effective dielectric constant that's going to be involved is going to be something more like 2.8 or 3, depending on the decay value of your PCB substrate. Now, if we use 2.8, you can see that the capacitance gets even lower. It's down to 1.8 picofarads. So that's a pretty small capacitance. If we then had this coplanar pair of conductors routing over a long distance, like let's say 10 inches, then we would get a lot more capacitance. We would get up to 18 picofarads, but you can still see it's pretty small. You have 18 picofarads potentially of capacitance on a large pair of conductors where you have them split from each other on the same layer in your PCB. Now, how does this compare to a parallel set of overlapping planes? So now here we're talking about two planes on different layers inside the PCB stackup. Well, let's take a look at this other calculator from Day Counter. I've defined the same two 1 inch by 1 inch plates overlapping each other by a distance of 0.1 millimeter or 4 mils, and we're using that same dielectric constant of 4. If we calculate that, we get a capacitance of 221 picofarads. That's a lot of capacitance. That's between a factor 10 and a factor 100 larger capacitance between those two plane layers. Now let's suppose this were a typical 4-layer board where we had those two planes on layer 2 and layer 3 separated by a thick core. Well, then in that case, our distance between the planes could be as large as 1 millimeter. If we then use that same 1 inch by 10 inch plate area, we would then have 10x larger plate area, as you can see here. And if we calculate the capacitance, you see that we get the exact same value, 221 picofarads. So what this all means is that the overlapping plane condition allows noise to much more easily pass between those two planes compared to the case where you have the two planes existing on the same layer in your PCB. Now, how does this compare to a typical Y-type capacitor, and what value should the Y-type capacitor have? Well, the value of your Y-type capacitor that you use in an isolated DC-DC converter needs to be larger than the winding-to-winding capacitance on that transformer in your design. The transformer winding-to-winding capacitance can vary depending on the construction materials that you use to build your transformer and the geometry of your transformer. So for example, planar transformers where the coils are basically overlapping can have very high winding-to-winding capacitance, and that demands that you use a larger Y-type capacitor. Typical values for a Y-type capacitor are 2 nanofarads. So a 2.2 nanofarad capacitor is just fine as long as you use a large enough voltage rating on that capacitor. So how do these capacitance values that we calculated for these plane pairs compare to a typical interwinding capacitance value for a transformer? Well, I have one of the transformers that we use in our Flyback transformer project on the bench on our LCR meter. Let's go ahead and take a look at that measurement right now. So here is our Flyback converter project. You can see I've been doing some rework on it. And then here we have the transformer that we used in that Flyback converter module. So let's go ahead and toss this thing onto our LCR meter. I'm hooking the probes up to the primary side. This is our inductance. So go back and watch that original video on our Flyback transformer design, and you'll see that we basically got this value in that video. Now let's go ahead and set this up for a capacitance calculation. We're going to have to hook up the probes here. So here you can see we have the capacitance measurement, and it measures 30.5 picofarads. So that's a lot smaller than the overlapping plane capacitance that we had in that calculation. It's also much smaller than the typical value that we would use for a Y-type capacitor by about a factor of 100. So as you can see from that measurement, we have a 30.5 picofarad capacitance across the transformer windings, but we have 221 picofarads of capacitance if we take our primary and secondary grounds and overlap them in the PCB stack-up. That's a significant difference. That means noise on one side of the DC-DC converter is 10 times more likely to go across the two planes than it is to go across the transformer windings when you have the two planes overlapping. And that's important because it shows that when you overlap those two planes in that DC-DC converter, you lose control of that noise path between the primary and the secondary side. Now, the whole point of splitting grounds is actually to control where the noise exists. And if you then do something in the PCB layout that causes you to lose control of that noise, it doesn't really make sense, does it? So clearly, from a noise control standpoint, it's actually much better to just cut out the planes through the entire stack up and create these different sections in your PCB layout for your primary and secondary sides of your isolated components. So let's take a look at what this looks like in an actual PCB layout. What we're going to do now is take a look at two past designs that we've shown on the channel. One is an isolated ADC module, and then the other is the PCB layout for that Flyback converter that I showed earlier in the video. So for the first design we're going to look at, I have here on screen our isolated ADC module. You can see what it looks like in 3D. And here if I put it in 2D, you can see we have all the copper layers visible. The ground nets have been split up by cutting the polygons all the way through the PCB stack up. Now, this design does not use an optocoupler. It uses an isolated analog to digital converter. And these components are used to take measurement of signals, sometimes low signal-to-noise ratio signals, in an environment where there is a risk of exposure to high voltage or just where you need to maintain galvanic isolation generally. And you can see that component is right here passing across this isolation gap. So it's pretty easy to see how this was done. If I scroll through the layers, you can see that we have identical polygons in this upper left corner passing all the way through the PCB stack up. Now, when we originally did this, I didn't place the Y-type capacitor across these ground nets, but doing that would actually be quite easy. If you just look here in 3D, there is a perfect place to put it. You could put it right here across this gap in this direction, or you could even put it right here going this direction, maybe just nudging this large capacitor to the right a little bit in order to make some room. But either way, you've got plenty of options for placing that Y-type capacitor if it's needed in this design. And probably for a Rev B, I will actually place that, put the updated files out there, and then you can go and download those for free off of my website. Next, let's take a look at the flyback converter module. This flyback converter module is of course an isolated DC-DC converter, and you can see here how the grounds are set up in 3D with this transformer. We have a cutout in the board, we have our ground on the right hand side for our 3.3 volt output, and then on the left hand side we also have our ground associated with the input. And here is where we have that optocoupler going right across this design. So there's an optocoupler here on the back side, part number LTV817. And if we just do a quick measurement across the pads, we can get an idea of the separation. It's actually 7 millimeters. So that's a lot larger than what was mentioned by Amit in his LinkedIn message. You can also see where I've placed the Y-type capacitor. It's going right here as component C12, and it links our primary side ground to our secondary side ground. Now, how does this capacitance from this Y-type capacitor compare to the case of coplanar grounds in that calculation that we saw earlier? Well, this is a 7.6 millimeter separation. So if we just go back in here and we take a look at what the capacitance would be with a 7.6 millimeter separation, and we have a 1 inch by 1 inch square set of conductors, you can see here that this capacitance is only 1.3 picofarads. So this should really illustrate why you want to have this Y-type capacitor bridging across these two grounds when you have this isolated DC-DC converter. Remember, the transformer in this design had a winding to winding capacitance of 30.5 picofarads. And that's a pretty typical number for most transformers that have that coil former structure. The capacitance across those two ground nets is 1.3 picofarads. And when we place that Y-type capacitor in the design, it has a capacitance of 2.2 nanofarads, so it's 1,000 times larger than the stray capacitance across those two conductors, and it's 100 times larger than the capacitance across the transformer. That gives you maximum noise control between the two sides of your DC-DC converter, and that's exactly why we set up the grounds this way in these types of designs. Thanks for watching this video, everybody. I always love getting your questions, especially on contentious topics like splitting grounds. So you can always send me a message on LinkedIn, or you can leave a comment in the YouTube comment section. And of course, if you leave a great comment or question, it just might end up in one of these videos. Thanks again for watching, everybody. Hit that like button, hit the subscribe button. You know where to leave the comments and questions. And last but not least, don't forget to call your fabricator, folks. We'll see you next time.